All right. Welcome to the last session of the first day of RecSys 2024. I'm Robin Burke. I'm be chairing this session. I have a couple of housekeeping questions. So are the authors, presenters present for the Laura paper? The second paper of this session, we didn't get a check-in from you all. Okay. And then also the last paper of the session from Netflix. Are the authors, presenters of that paper in the room? I don't see any hands. Okay. I'm going to assume those folks are arriving late. And so that means we will have to do the papers a little bit out of order. We never got the slides for the first presentation, so that presentation will not be happening this afternoon. And I do not see the authors for paper number 2. So we are going to be starting a little bit out of order. We will be starting with a paper entitled Instructing and Prompting Large Language Models for Explainable Cross-Domain Recommendations. And I believe we have 2 presenters, Cataldo Musto and Alessandro Petruzzelli, whose name is the same as the theater we're in. So that's something special.
Thank you, Robin, for the introduction. Alessandro has no connection with the theater at all. I want to be sincere about this. So, good afternoon, everyone. I'm happy to show you our work about instructing and prompting large language models for cross-domain recommendations. So, in this paper, we will mainly talk about, of course, cross-domain recommendations. So, as we know, the idea behind cross-domain recommendation is very straightforward. We have user preferences in a base domain, movies, for example, and we want to provide recommendation in a different domain. So we have preferences about movies, and we want to provide recommendations about books. The problem that we typically have with cross-domain recommendations is related to data sparsity, because it's quite hard to have enough information about preferences of the users in both the domains, so about both movies and books. So it's not easy to implement effective solutions for this problem. The intuition that we have and we tried to address through this work is quite intuitive. So we try to exploit large language models to tackle this task, because the intuition, again, behind this work is that the knowledge that we need to identify the connections that we have between items in different domains is probably already encoded, already injected into large language models in their training, so we can easily exploit it to provide users with cross-domain recommendations. So the research question that we try to address, of course, is this one. So whether and how we can exploit the knowledge that is encoded in LLMs, such as GPT, Llama, Mistral, and so on and so forth, to tackle this task. Let's go to the methodology. Here you have a very general representation of the framework that we implemented to tackle this task. The very intuitive idea that we tried to implement through this mechanism is to transform the information that we have in data sets for cross-domain recommendation and to inject this kind of knowledge into an LLM through fine-tuning or retraining of the model to seamlessly generate some cross-domain recommendations. Basically, our methodology is split into 3 steps. The first one is a pre-processing step, where we start by the data that we have, and we, let's say, transform or lexicalize the data to make them suitable in a form that can be injected into an LLM. Next, in the second step, we use all this information to do instruction tuning. So we take all the prompts that we have designed, all the content that we have generated based on the cross-domain data sets to create, to retrain the model, to fine-tune the model, to make it able to better tackle the cross-domain recommendation task. Finally, the third step is the recommendation step, where we are able to prompt the model that we have learned and to create, to return a cross-domain recommendation together with a suitable explanation. So, first step. In the first step, we start by processing the data. Of course, one important thing to be pointed out here is that we have split for this step the users that we have in our data set into two groups. This was done to avoid any kind of data leakage. So we want that the user that we use to retrain the model, to fine-tune the model, is different with respect to the set of the users that we use to, of course, just evaluate the performance of the system. So in the pre-processing phase, as I said, we have just transformed data set for cross-domain recommendation in a form that is suitable by an LLM. So we designed this kind of prompt where we use the system prompt to basically give the cross-domain recommender system information about how it should behave. So about the task to be done, about the format of the information that it will receive as input, and about the kind of output that it shall generate. Next, in the user prompt, so the first part is basically fixed, so it's the same for all the prompts that we create. The second part, of course, is dynamic and based on the information that we have in the datasets, and is populated, as you can see, based on the preferences of a generic user that we have. So we have information about what the user has liked in a base domain, what the user disliked in a base domain, together, as you can read, with some descriptive features that we have. And finally, we have the task to be carried out, so the set of the items to be ranked in the target domain. This kind of setting is quite popular for recommendation based on LLM, so it's basically a ranking task. And it was chosen to avoid any kind of hallucination by the model. The output of the model, of course, is a ranking of the items together with an explanation that is generated by the LLM. This kind of process is repeated for all the users that we have in our data sets and for all the domains that we have. So we create in a form that is, again, suitable by LLMs, all the data that we have in the original data sets. In the second step, we use all these prompts that we have designed to fine-tune the LLM. So we start by an LLM such as Llama or Mistral, as we will show later in the experiments, and we create our CDR LLM, so LLM fine-tuned for our specific task. Of course, as I have said, in this step, we just focus on one portion of the users that we have in our data. What we do in the fine-tuning step is basically a complete retraining of the model, where we, of course, try to minimize the error on this function. So we want to find the parameters that allow us to better rank the items. So we want that the model learns how to rank the items in the correct way based on the prompt that we have. Finally, in the recommendation step, we have the prompting phase. So we start by the LLM that we have learned, and we basically query the LLM with a new prompt that, of course, follows the same structure. And we generate a recommendation, so a set of ranked items in the target domain, together with a suitable explanation that can support the recommendation. So basically, this is the idea that we have carried out in the paper, and I leave the stage to to Alessandro to discuss the results that we got.
Okay, so thank you, Cataldo. Let's start with the experimental design. We aim to answer to 3 research questions. The first one is about the test to evaluate the effectiveness of our methodology. So, as Cataldo just said, we implemented this methodology and we tested on 3 different LLMs, Llama 2, Mistral, and GPT 3.5. We fine-tuned Llama 2 and Mistral, and we use GPT 3.5 as it is. For the second question, we perform some, let's say, some ablation study because we want to evaluate the effect of in-context learning. So we tested all the 3 models in both 0-shot and 1-shot learning. So we provide an input-output example in 1-shot learning. And then, of course, we have the comparison with the state-of-the-art. We tested our methodology in different cross-domain scenarios that you can see here. All these scenarios have been obtained by filtering the Amazon datasets. And concerning the evaluation, we use a set of metrics that includes precision, recall, F1 for the accuracy. Then we have NDCG for the ranking and the average popularity. We try to evaluate also the clarity of explanation by evaluating the perplexity. All the baseline that we consider are already have been optimized and are already implemented in RecBall cross-domain framework, so we use that baseline. And okay, now we are ready to check the results. Of course, here we reported only a small set of results because they are a lot of, we have a lot of scenarios, but if you read the paper, you can find all the results. So let's start with scenarios where movies are in the base domain. So we give user preferences in movie domains, and then we obtain recommendation in books and CDs. As we can see here, basically GPT achieved the best performance in these settings, but we cannot say the same when we change the base domain. For example, in this case, we have that CDs are in the base domain, and here we can see that generally Llama achieved best performance, and the same we can say for domains where books are in the scenarios where books are in the base domain. This can clearly, based on this result, we can clearly say that our methodology as is effective because we can adopt the smaller model because GPT and Mistral are smaller than, wait a second, Llama and Mistral are smaller than GPT, and we can have more or less comparable results. And these are some example of explanation. As we can see here, GPT provides longer explanation, including some aspects that we have prompted in the prompt. For example, some features of the items. Generally, Llama provides smaller explanation, let's say shorter explanation. And to answer the second question, here we are reported a couple of plots where we can see that GPT is the model that benefits the most from in-context learning, because we can clearly see that when we provide one example only, this boosts the performance of GPT. And lastly, here are the results, the comparison with the state-of-the-art. As we can see, here we only report our best method within respect to the state-of-the-art, but this conclusion can be generalized over different models and our different models and different scenarios. So how we can see here, GPT achieved mostly in the most of metrics the best performance. is a significant improvement is reported in NDCG, and these results are confirmed by this second example scenarios, that movies to books, where GPT achieved best performance in all metrics except for the average popularity. So let's try to conclude and sum up the outcome of this paper. So basically, we have implemented, tested a new approach, a framework that can be used to adapt LLM in solving, in handle cross-domain recommendation, and we have proved that is effective. We have noticed that when we tune a model, we have an effect also on the average popularity and on the bias, so we can reduce the bias if we tune a model to handle the recommendation task. And lastly, one of the reasons to use LLM to get recommendation is because they can naturally provide an explanation that can help. And that's it. Thank you.
All right, I will take a look at the app, but while we are doing that, oh, actually I see a question here. Asking if you compare this approach to more classical kinds of recommendation and explanation.
Sorry? I don't understand. Can you repeat, please?
Oh, okay, actually, I think that was an older question sitting here. Okay, looking at your training data, which includes the IDs of books and their descriptions, the system is not able to recommend any book that is outside of the prompting data set. Is that correct?
Yeah, it's correct. We just focused on the ranking of the books that we have because we needed some kind of ground truth, basically, to evaluate the performance of the system. If we remove that part of the prompt, it can also generate something that is out of the original data sets.
And those, you don't have like a separate recommendation process to produce that short list. That was kind of coming from the data. Is that correct? Yeah. Yeah. Okay. Okay. So another question here. The performance might be related to the format of the system prompt, which, I think that part of what you were doing was trying to come up with good prompts. Have you performed an evaluation study to verify whether the results were dependent of the system prompt? Different formulations of the prompt to see, what had the biggest impact.
Actually, we did not evaluate any variant of the system prompt. We made some experiment by changing the set of descriptive features we use to describe the items the user liked and not liked. And yeah, there is some results on the paper, but yeah, no, the system prompt was the only one we considered in the experiments.
Okay. We maybe have time for a short question from the floor, if there is one. I don't see any hands. Okay, let's thank our speakers.